Something out there is moving toward us. Scientists detected it 3 years ago. They said nothing publicly. The data was checked, rechecked, and locked behind closed doors while researchers tried to understand what they were looking at. The object or signal or structure, no one agrees on what to call it yet, is traveling through the void between galaxies. It is moving in a way that gravity alone cannot explain, and its trajectory, when traced forward, intersects with our region of space. Not tomorrow, not in a human lifetime, but on a cosmic timescale that makes astronomers deeply, quietly uncomfortable. You are about to see why this discovery has triggered the most urgent scientific conversation in decades, why telescopes on 3 continents are now pointed at the same patch of darkness, and why the silence around this object may be the most unsettling part of all. We need to start with what deep space actually means, because the thing moving through it is not where anything should be moving at all. Picture the space between galaxies, not the space between stars, which is vast, but still part of a galaxy's structure. The space between entire galaxies, intergalactic space. It is the most empty environment in the known universe. No stars, no planets, no gas clouds dense enough to collapse into anything. Just hydrogen atoms scattered so thinly that you would need to travel thousands of miles to encounter a single one. The temperature hovers a few degrees above absolute zero. Radiation from the cosmic microwave background, the faint afterglow of the Big Bang, is the only thing moving through it in any significant quantity. And even that is barely a whisper. Objects do not naturally travel through intergalactic space. Galaxies themselves are bound by gravity into clusters, and those clusters into superclusters, all threaded together by vast filaments of dark matter. But individual objects, rogue stars, planets, asteroids, almost never escape their home galaxies with enough velocity to cross the void. The energy required is extraordinary. A star would need to be flung out by a supermassive black hole or a catastrophic collision. Even then, most would not make it far before being recaptured by gravity. What travels through intergalactic space, when anything does, moves in predictable ways. Gravity governs everything. Trajectories follow curves determined by mass and velocity. There are no surprises. The equations are centuries old. They work. That is what made the detection in 2021 so difficult to process. The object was there. It was moving. And it was not following the rules. The first hint came from a radio observatory in Western Australia, the Australian Square Kilometre Array Pathfinder, a collection of 36 dish antennas designed to map hydrogen gas across the universe, was conducting a routine deep field survey. Radio telescopes do not take pictures the way optical telescopes do. They detect radio waves, a form of light with wavelengths far longer than what your eyes can see. Those waves carry information about the objects emitting them: temperature, magnetic fields, motion. The survey was mapping neutral hydrogen, the most abundant element in the universe. Hydrogen emits a specific radio signal at a wavelength of 21 centimeters. By detecting that signal across vast regions of space, astronomers can trace where gas is concentrated, where galaxies are forming, and where the cosmic web structure lies hidden. In March 2021, the survey flagged an anomaly, a radio signal at the correct wavelength for hydrogen, but coming from a region of space between 2 galaxy clusters where no significant hydrogen concentration should exist. The signal was faint but persistent. It appeared in multiple observation passes. It was not noise. When the team processed the data more carefully, they found something stranger. The signal was redshifted, meaning the source was moving away from us as space expands. That part was normal. Every distant object in the universe is redshifted. But the degree of redshift was wrong. It placed the object in a region of intergalactic space, roughly 300 million light-years from Earth, far outside any galaxy, traveling at a velocity inconsistent with the local gravitational field. The signal was not stationary. Follow-up observations over the next 6 months showed it was moving. Slowly but measurably, the change in position was tiny, but detectable across the resolution limits of the array. When researchers calculated the trajectory, they realized it was not following a gravitational arc around any nearby mass. It was moving in a straight line, or close to it. Straight line motion through intergalactic space is not normal. Objects in space do not move in straight lines unless something pushed them hard. The team published a preliminary paper in a low-profile journal, flagging the detection as an unidentified transient radio source. The paper was technical, cautious, and mostly ignored. Then 2 other observatories detected the same thing. The first was the Very Large Array in New Mexico, one of the most sensitive radio telescope networks in the world. In August 2021, during an unrelated survey of the same region of sky, the VLA picked up the signal independently. The position matched, the velocity matched, the anomaly was real. The second detection came from something unexpected: the Hubble Space Telescope. Hubble does not detect radio waves. It observes visible and ultraviolet light. But in October 2021, Hubble was conducting deep field imaging of a distant galaxy cluster in the same general region of sky. When astronomers processed the images, they found a faint point of light in the intergalactic space between the cluster and our position. It was extraordinarily dim, barely above the noise threshold, but it was there. When they cross-referenced its position with the radio signal, the match was undeniable. Same location, same distance, same trajectory. Whatever was emitting the radio signal was also emitting faint visible light. That changed everything. Radio signals can come from many sources: cold gas clouds, pulsars, distant quasars, even instrument artifacts. But a source emitting both radio waves and visible light in intergalactic space, moving at high velocity, with no obvious gravitational explanation for its trajectory, was something else entirely. The international collaboration that formed around this detection included researchers from 11 countries. They did not go public. They filed observing proposals with every major telescope that could contribute data, and they started trying to figure out what they were looking at. The first question was simple. What is it? The object is not a star. That was the first conclusion, and it was definitive. Stars emit light because nuclear fusion in their cores produces enormous amounts of energy. That energy radiates outward, creating the heat and brightness we associate with stars. The spectrum of light from a star, its rainbow of colors, when broken apart by a spectrograph, carries a very specific signature. It shows absorption lines where elements in the star's outer layers absorb specific wavelengths of light. Those lines are like fingerprints. Every star has them. The object's spectrum did not match. Hubble captured enough light over multiple long exposure observations to build a rough spectrum. The light was continuous, not marked by the absorption lines that stars produce. It was dim and red, consistent with something reflecting or scattering light rather than generating it internally. That ruled out any kind of self-luminous object, like a star or a quasar. The next possibility was a rogue planet. Planets ejected from their home solar systems by gravitational interactions with larger bodies can be flung into interstellar space, and in rare cases, intergalactic space. These rogue planets are incredibly difficult to detect because they emit no light of their own. They can only be seen if they reflect light from a nearby star or if they pass in front of a background light source, briefly blocking it. The reflected light model was initially promising if the object was a large planet or a brown dwarf, a failed star, not massive enough to ignite fusion. It could in theory reflect enough light from distant stars to produce a faint signal, but the radio emission did not fit. Planets do not emit strong radio signals unless they have powerful magnetic fields and are interacting with charged particles like Jupiter does with its magnetosphere. In the emptiness of intergalactic space, there are no charged particles to interact with. The radio signal should not exist. That left 2 categories of explanation. Either the object was artificial, or it was something natural that we had never seen before. The artificial hypothesis was not taken seriously at first. It is the least likely explanation for almost any astronomical anomaly, and for good reason. The universe is full of natural phenomena that can mimic what human imagination associates with artificial activity. Pulsars, when first discovered, emitted such regular radio pulses that astronomers briefly considered whether they might be alien beacons. They were not. They were rapidly spinning neutron stars. Oumuamua, the interstellar object that passed through our solar system in 2017, had an elongated shape and a trajectory that some speculated could indicate artificial origins. Follow-up analysis showed it was almost certainly a natural object. likely a fragment of a comet from another star system. Science applies Occam's razor rigorously. The simplest explanation that fits the data is preferred until the data rules it out. Artificial origin is never the simplest explanation. It requires the existence of technology, which requires the existence of intelligent life, which requires an entire chain of biological and evolutionary assumptions that natural explanations do not. But the artificial hypothesis did not go away. It stayed on the table, unspoken in most of the early papers, mentioned only in private conversations between researchers, because the radio mission had structure. When the VLA analyzed the signal in detail, it was not a simple continuous tone. It was modulated. The intensity varied in a pattern that repeated roughly every 4.3 hours. The variation was subtle, only a few % change in strength, but it was regular. That kind of regularity is not impossible in nature. Pulsars are perfectly regular. Rotating objects with uneven surfaces or magnetic fields can produce periodic signals, but combined with the trajectory, the lack of a clear natural source, and the faint optical component, the structured signal was enough to keep the question open. The team did what scientists always do when faced with an unexplained signal. They looked for natural explanations first. One possibility was that the object was a fragment of a neutron star, ejected during a supernova and somehow flung into intergalactic space. Neutron stars are extraordinarily dense remnants of massive stars that exploded. A fragment, even a small one, would carry intense magnetic fields and could emit radio waves as it rotated. But neutron star fragments should also emit X-rays, and pointed observations with the Chandra X-ray Observatory found nothing. No X-ray signal at all. Another possibility was a magnetar, a type of neutron star with an exceptionally strong magnetic field. Magnetars can emit powerful bursts of radio waves and visible light during magnetic reconnection events. But magnetars are not known to travel through intergalactic space at high velocity, and their emissions are typically irregular and violent. This signal was steady, periodic, and calm. A third idea was that the object was a compact cloud of ionized gas, glowing faintly from residual energy after being stripped from a galaxy during a collision. Galaxy collisions can fling enormous amounts of gas into the intergalactic medium. That gas can stay ionized for millions of years, emitting faint radio and optical light. But gas clouds do not move in straight lines. They disperse. They follow the gravitational field of the surrounding matter. This object was not dispersing. It was compact, coherent, and moving with purpose. Every natural explanation had a fatal problem, something that ruled it out or left a critical piece of the data unexplained. The researchers kept looking. And then the trajectory analysis came back. The trajectory was calculated independently by 3 different teams using different methods. All 3 arrived at the same result. The object is moving toward us, not directly. Space is 3-dimensional, and the object's path does not intersect Earth's current position. But when you account for the motion of our solar system around the center of the Milky Way, and the motion of the Milky Way itself through space, and the object's velocity vector, the paths converge. In roughly 3 million years, the object will pass through the outer regions of the Milky Way galaxy. It will not hit us, but it will enter our gravitational neighborhood. 3 million years sounds like an eternity. On human timescales, it is incomprehensible. On cosmic timescales, it is a blink. The Milky Way is over 13 billion years old. 3 million years is 0.02% of that. It is close, astronomically close. The object's velocity is approximately 400 kilometers per second relative to the local reference frame of intergalactic space. That is fast, but not impossibly so. Stars in the Milky Way's halo move at similar speeds. Rogue stars ejected from the galactic core by interactions with the central supermassive black hole can reach velocities even higher. But those stars are inside the galaxy. This object is outside, moving through a region where nothing should be moving that fast without a clear gravitational source to explain it. When researchers traced the trajectory backward, they found something even stranger. The object did not originate from any nearby galaxy. Its path, when extended backward in time, points toward a region of deep intergalactic space between the Virgo supercluster and the Hydra Centaurus supercluster. There is nothing there, no major galaxy. No galaxy cluster. No obvious source. It came from nowhere. That is not a figure of speech. Based on its velocity and the time it would take to cross the distance from the nearest significant gravitational source, the object has been traveling for at least 100 million years, possibly much longer. It is old. It has been crossing the void for longer than complex life has existed on Earth. The team modeling its trajectory ran simulations to test whether any known astrophysical event could have produced this motion. Supernovae can eject material at high speeds, but not coherent objects of this size moving in straight lines across intergalactic distances. Colliding galaxies can fling stars and gas into the intergalactic medium, but those ejections follow gravitational arcs, not straight-line trajectories. Binary black hole mergers can produce gravitational recoil kicks that fling black holes out of their host galaxies, but black holes emit no light. This object is emitting both radio and optical signals. Every simulation required an initial acceleration event that the known laws of astrophysics struggle to produce naturally. One researcher, speaking off the record, described the trajectory as ballistic. That word carries weight. Ballistic implies intent. It implies something was launched. The word appeared in internal correspondence between team members. It did not appear in any published paper. The team submitted their findings to a major astrophysical journal in early 2023. The paper was titled An Unidentified Radio and Optical Transient in Intergalactic Space with Anomalous Kinematics. It was accepted after peer review and published in June 2023. The paper was measured, careful, and hedged with appropriate scientific caution. It concluded that the object's nature remained unresolved and that further observations were needed. The paper was noticed by the broader astronomical community immediately. Within weeks, observing time on multiple telescopes was reallocated to study the object in more detail. The James Webb Space Telescope, the most powerful observatory ever built, was pointed at it. What Webb found made the mystery considerably worse. Webb observes the universe in infrared light. It was designed specifically to see objects too faint, too distant, or too cool for other telescopes to detect. When it turned its instruments toward the object's coordinates in September 2023, it gathered more light in a single exposure than Hubble had collected over months. The resulting data was extraordinarily precise, and it was deeply strange. The object is small. Webb's infrared imaging resolved it as a point source, meaning it is smaller than the resolution limit of the telescope. That places an upper bound on its size of roughly a few hundred kilometers across, possibly smaller. For comparison, Earth's diameter is about 12,700 kilometers. This object, whatever it is far smaller. Closer in size to a large asteroid or a small moon. The infrared spectrum revealed composition. Webb's spectrograph broke the object's light into its component wavelengths, creating a detailed chemical fingerprint. The spectrum showed absorption features consistent with silicate minerals, rock-forming compounds made of silicon and oxygen, the same kinds of minerals that make up Earth's crust, the Moon, and most rocky bodies in our solar system. This was the first definitive evidence that the object is solid, but there was another feature in the spectrum that no one expected. A faint emission line at a wavelength corresponding to ionized hydrogen. Hydrogen emitting light because it has been heated or energized by something. That emission was coming from a thin cloud of gas surrounding the object, not the object itself, a cloud around it. Gas clouds do not naturally surround small rocky objects in the vacuum of intergalactic space. There is no source of gas out there, no atmosphere to hold it in place, no gravitational field strong enough on an object that small to retain gas over millions of years, and yet the gas was there, detectable, real. The emission was faint, but it had structure. The hydrogen was not evenly distributed around the object. It was concentrated on one side, the side facing the object's direction of travel, like a faint bow wave, as if the object was moving through something, compressing gas in front of it as it went. But intergalactic space is effectively empty. There is no gas dense enough to compress into a visible bow shock at the velocities this object is traveling. The density of hydrogen in intergalactic space is roughly 1 atom per cubic meter. You would need to be moving at relativistic speeds, close to the speed of light, to compress that into anything detectable. The object is moving at 400 kilometers per second. Fast by human standards, nowhere close to relativistic. The bow shock should not exist. One explanation, proposed cautiously in internal team discussions, was that the object itself is emitting gas. Outgassing, like a comet. Comets are icy bodies that release gas and dust when heated by a star's radiation, creating the characteristic glowing tail. But this object is in intergalactic space. There is no nearby star, no radiation source intense enough to heat it. And the outgassing, if that is what it is directional. Comets release gas in all directions. This is releasing it forward, into its direction of travel. That pattern is consistent with propulsion. The word appeared in a single email exchange between two members of the Webb observation team. It was not included in any official report. It was not spoken aloud in meetings. But it was thought about. Because once you see the data, the question becomes unavoidable. If the object is emitting gas in the direction of its travel, and if that emission is producing a detectable signal, then the gas is carrying energy directed opposite to the object's motion. That is what a rocket does. It expels mass in one direction to produce thrust in the other. Propulsion, the amount of thrust required to maintain the object's velocity over millions of years, is extraordinarily small. Intergalactic space has no drag, no friction. Once an object is moving, it stays moving. The tiny amount of gas Webb detected would be more than enough to sustain the trajectory if it had been released continuously over the object's travel time. This is speculative. It is the least probable explanation. It requires assumptions that have not been confirmed. But it fits the data better than any natural explanation proposed so far. The team did not publish these findings yet. They are waiting for more data. Webb is scheduled to observe the object again in early 2025, with longer exposure times and more sensitive instruments. Other telescopes are also targeting it. The data is accumulating. The picture is getting sharper, and the object is still moving. The radio emission has structure. That fact alone is not extraordinary. Many natural objects emit structured radio signals. Pulsars are the most famous example. They are rapidly rotating neutron stars with intense magnetic fields. As they spin, they emit beams of radio waves from their magnetic poles. If one of those beams sweeps across Earth, we detect a pulse. Regular, precise, entirely natural. The object's radio signal is not like a pulsar. It is not a series of sharp pulses. It is a continuous emission with a periodic variation in intensity. The signal rises and falls over a cycle of roughly 4.3 hours. The variation is smooth, not abrupt. It looks like a sine wave, a pattern that repeats perfectly over and over. That periodicity suggests rotation. If the object is spinning, and if one side of it emits more radio energy than the other, we would see the signal strengthen and weaken as that side rotates in and out of view. That is a natural explanation. It is the simplest one. But the period is strange. 4.3 hours is fast for an object of the size Webb observed. Most asteroids rotate with periods measured in hours to days, depending on their size and shape. Smaller objects can spin faster, but there is a limit. Spin an object too fast and centrifugal force tears it apart. The tensile strength of rock can only hold so much. Researchers calculated the maximum rotation speed for a rocky object of the size Webb measured. The limit depends on the object's density and structural integrity, but for solid rock, the shortest stable rotation period is roughly 1 hour. Below that, the object breaks apart. The observed 4.3-hour period is well within the safe range, but it is on the faster end of what natural rotation would predict for something that size. That fast rotation could have a natural explanation. A collision in the distant past could have imparted angular momentum, setting the object spinning. Gravitational interactions during ejection from a galaxy could also produce rapid rotation. Neither explanation is ruled out. What is harder to explain is the signal's stability. The 4.3-hour period has not changed. Observations conducted over a span of 2 years show no measurable drift. The signal repeats with extraordinary consistency. Natural rotating objects slow down over time. Friction, tidal forces, and internal dissipation gradually reduce rotation speed. The process is slow, but over millions of years, It is significant. If the object has been traveling for 100 million years, its rotation should have slowed measurably. It has not. The alternative is that the rotation is being maintained. That requires energy. A natural source of internal energy could come from radioactive decay of heavy elements in the object's core. Some asteroids retain enough internal heat from their formation to remain geologically active for billions of years. That heat could, in principle, drive processes that maintain rotation, but the amount of energy required is small, almost negligible, and the mechanism by which internal heat would maintain spin is unclear. All the energy is being supplied externally. That opens the door to explanations that scientists are reluctant to discuss publicly, but cannot ignore privately. The signal's frequency is also worth noting. The radio emission is centered at approximately 1.42 GHz. That is the hydrogen line, the most common naturally occurring radio frequency in the universe. Hydrogen, the simplest and most abundant element, emits radio waves at this frequency. When its electron flicks from one spin state to another, it is the frequency radio astronomers use to map hydrogen across space. It is also the frequency that SETI, the Search for Extraterrestrial Intelligence, monitors most closely. Because if an alien civilization wanted to send a signal that would be noticed by anyone looking, 1.42 GHz is where they would broadcast. It is the universal channel, the frequency that any scientifically literate civilization would recognize as intentional. The object is transmitting at that frequency, continuously, with a regular, repeating modulation moving through intergalactic space toward the Milky Way. The SETI Institute was notified of the detection in late 2023. They did not issue a public statement. Internal communications later leaked showed significant interest. Follow-up observations were conducted using the Allen Telescope Array in California, a network of 42 radio dishes dedicated to searching for extraterrestrial signals. The array detected the object's radio emission clearly. The modulation was confirmed, and the signal showed no additional complexity, no substructure, no embedded information in the modulation pattern, just a regular rise and fall in intensity. The lack of complexity is either reassuring or meaningless. A true artificial signal designed to communicate information would likely carry encoded data, patterns within patterns, structures that stand out against natural noise. This signal, as far as current analysis can determine, does not. It is periodic but simple. That points toward a natural origin, or it points toward a signal that is not designed to communicate information. A beacon, a marker, something meant to be noticed but not decoded, a signal that says, "We are here." Nothing more. The debate is ongoing, the data is real, the interpretations are provisional, and the next layer of evidence is about to make the question far more urgent. Let's separate confirmed observations from speculation. The line between them matters. Confirmed, an object exists in intergalactic space, approximately 300 million light-years from Earth. It is emitting both radio waves and faint visible infrared light. It is small, likely a few hundred kilometers across, and composed primarily of silicate rock. It is surrounded by a thin cloud of ionized hydrogen gas, concentrated on the side facing its direction of travel. It is moving at approximately 400 kilometers per second through intergalactic space. Its trajectory, when traced forward, will bring it into the outer regions of the Milky Way galaxy in roughly 3 million years. Its radio emission is periodic, with a cycle of 4.3 hours, and is centered at the hydrogen line frequency of 1.42 GHz. The signal has remained stable over at least 2 years of observation. No X-ray emission has been detected. Confirmed. The object's trajectory does not match any natural ejection scenario modeled so far. Its origin point, when traced backward, lies in deep intergalactic space with no obvious source galaxy. Its motion is consistent with ballistic travel and initial acceleration event, followed by coasting through empty space, unconfirmed but under serious consideration. The object may be outgassing in a directional manner consistent with low-level propulsion. The gas cloud surrounding it may be the result of active emission rather than environmental interaction. The rotation period may be artificially maintained rather than naturally decaying. Unconfirmed and speculative. The object may be artificial. The signal may be intentional. The trajectory may be deliberate. The reason these distinctions matter is that science does not proceed on speculation, it proceeds on evidence. The evidence is accumulating. The speculation is growing because the evidence keeps pointing in uncomfortable directions. But the two are not the same. What comes next is more data. The James Webb Space Telescope will observe the object again in 2025. Longer exposures, more detailed spectroscopy, higher resolution imaging. If the object is outgassing, Webb will detect the chemical composition of that gas. If the outgassing is directional and sustained, that will be measurable. If the rotation period has changed even slightly, that will be detectable. The Very Large Array is also planning a deep observation campaign. They will monitor the radio signal continuously for several months, looking for any variation beyond the 4.3-hour cycle. If there is additional structure in the signal, that will reveal it, and there is another telescope coming online that changes the game entirely. The Square Kilometre Array is the largest radio telescope ever built. When fully operational in 2028, it will consist of thousands of individual antennas spread across 2 continents, Australia and South Africa, working together as a single instrument. Its total collecting area will be 1 square kilometre, hence the name. That is roughly 50 times more sensitive than any existing radio telescope. SKA is designed to map the entire sky in radio wavelengths with unprecedented detail. It will detect hydrogen across the universe, trace the formation of the first stars, and study the magnetic fields of distant galaxies. It will also, almost certainly, see things no one predicted. The object moving through intergalactic space is now a priority target for SKA once the array reaches full sensitivity. When SKA observes it, the radio signal will be resolved in far greater detail than anything currently possible. If the 4.3-hour modulation carries substructure, SKA will find it. If the signal varies over longer timescales, SKA will detect that too. If the object is emitting multiple frequencies beyond the primary hydrogen line, SKA will measure them. SKA will also be able to detect far fainter signals. If the object is emitting directed radio beams, not just omnidirectional broadcasts, SKA may see those beams directly. If there are other objects like this one traveling through intergalactic space too faint for current telescopes to detect, SKA will find them. The possibility that this object is not alone is one of the quietest and most significant questions in the entire investigation. If one object like this exists, it is an extraordinary anomaly. If there are others, the picture changes entirely. No additional objects have been confirmed yet. But the search has only just begun. The region of sky where this object was detected is now being surveyed more intensively than almost any other patch of intergalactic space. Multiple teams are looking. The data is being processed, and the statistical analysis is underway. One preliminary study, not yet peer-reviewed, analysed archival radio survey data from the past decade. The researchers were looking for transient signals in intergalactic space that might have been overlooked because they did not fit the profile of known object types. The study flagged 17 candidate detections. Most were ruled out as instrumental artifacts or distant background sources. 3 remain unresolved. Those 3 candidates are all in regions of intergalactic space with no obvious natural sources. All 3 are faint. All 3 show periodic modulation in their radio emission, and all 3, when their trajectories are estimated from the limited data available, appear to be moving. If those detections hold up under scrutiny, the object we have been discussing is not unique, it is part of a population. And that changes the question entirely. A single anomalous object moving through intergalactic space can be explained, with difficulty, as a rare natural event. A population of such objects cannot. Populations imply a common origin, a shared mechanism, a source that produces them in numbers large enough that we are now beginning to detect them. The follow-up observations of those 3 candidates are scheduled for 2025. The telescopes are ready. The data will arrive, and the answer to whether this object is alone will be known within the next 2 years. The implications of that answer are profound. If the object is alone, the investigation remains focused on explaining a single extraordinary anomaly. If it is not alone, the investigation shifts to a far larger question. What is producing these objects? Where are they coming from? And what does it mean that they are moving through space in ways that gravity alone does not explain? The trajectory analysis is the next piece of the puzzle, and it may be the most unsettling one yet. Objects in space move according to gravity. That is the foundation of celestial mechanics. Every planet, moon, asteroid, comet, star, and galaxy follows a path determined by the gravitational influence of the mass around it. The equations governing those paths were written by Isaac Newton over 300 years ago and refined by Albert Einstein a century ago. They work. They predict the motion of objects across the solar system with extraordinary precision. They predict the orbits of planets around distant stars. They predict the paths of galaxies as they move through the universe. When an object's motion does not match the gravitational field it is moving through, something is wrong. Either the mass creating the gravitational field is not where we think it is, or something else is acting on the object. The object moving through intergalactic space has a trajectory problem. When researchers calculated the gravitational field of the region it is traveling through, using the known positions and masses of nearby galaxies, galaxy clusters, and the large-scale distribution of dark matter, the expected motion did not match the observed motion. The object is moving too straight. Gravity bends paths. It pulls objects toward mass in the region of space where this object is traveling. The nearest significant mass is the Virgo supercluster, a collection of thousands of galaxies including our own Milky Way. The object should be falling toward it, slightly. The effect would be small, but measurable over the distances and timescales involved. It is not. The object's trajectory shows no measurable curvature toward the Virgo supercluster. It is moving as if the supercluster's gravity does not exist. That is not possible under standard gravitational physics unless the object was accelerated to a velocity high enough that the gravitational pull is negligible over the time frame we are observing, but that requires an initial acceleration event of extraordinary energy, far more than a supernova or any known astrophysical explosion could provide to a solid object. One explanation is that the object was accelerated recently, within the past few million years, close enough in time that it has not yet had time to curve noticeably under the supercluster's gravity. That would explain the straight trajectory, but it requires a recent acceleration event, and there is no sign of one. No supernova remnant, no ejection event from a nearby galaxy, nothing. Another explanation is that the object is still being accelerated continuously. A tiny thrust applied over millions of years could maintain a straight line trajectory, even in the presence of gravitational fields. The thrust required is small, far smaller than any rocket humans have ever built, but sustained over millions of years, it is enough. That explanation requires a power source. Natural power sources for objects in space are limited. Radioactive decay of heavy elements produces heat, but not directed thrust. Outgassing from a comet produces thrust, but requires volatile materials like water ice, which sublimate when heated. In the cold of intergalactic space, with no nearby star to provide heating, outgassing should have stopped millions of years ago. Unless the outgassing is not driven by external heating, unless it is driven by something internal, a power source inside the object that is still active. The amount of power required is extraordinarily small, less than a kilowatt, about the same as a household space heater. Sustained over millions of years, that tiny amount of power is enough to explain the trajectory. Radioactive decay could provide that power. A rocky object with enough uranium, thorium, or other long-lived radioactive elements in its core could generate heat for billions of years. If that heat is venting through cracks or vents in the object's surface, it could release gas in a directional manner. The object becomes, in effect, a natural low-thrust rocket. Slow, patient, crossing the void over timescales no human mission could ever achieve. This is a natural explanation. It fits the data. It is the simplest explanation that does not require artificial origin, and it is being taken seriously by multiple research teams. But it has a problem. If the outgassing is driven by internal radioactive decay, the gas being released should be chemically consistent with volcanic or geothermal emissions. Water vapor, carbon dioxide, sulfur compounds, Webb-detected hydrogen, ionized hydrogen. That is not what radioactive decay produces. Hydrogen is the simplest element. It is everywhere in the universe, but it is not a product of geological outgassing from rocky bodies. Earth's volcanoes do not emit pure hydrogen. Mars's ancient volcanic vents did not release hydrogen. The Moon has no hydrogen outgassing. Hydrogen comes from the primordial material of the universe, from gas clouds in space, or from nuclear processes. If the object is releasing hydrogen, it is either carrying hydrogen in some stored form, which is possible but requires explanation, or it is producing hydrogen through a process we do not understand. The trajectory problem does not have a clean answer. Every explanation requires assumptions that stretch the boundaries of what we consider normal. And the object is still moving. The next observation window opens in 3 months. Webb will point its instruments at the object again, and this time the team knows exactly what to look for. They will measure the hydrogen emission in detail. They will look for any other gases mixed with it. They will analyze the temperature of the gas to determine whether it is being heated or simply released cold, and they will measure the object's position with extraordinary precision to see if the trajectory has changed at all. If the trajectory has changed, even by a fraction of a degree, it will tell us something. If it has curved toward the Virgo supercluster, the object is behaving normally, and the straight line motion we have seen so far is simply a short-term snapshot of a longer gravitational arc. If it has curved away from the supercluster, something is very wrong. And if it has maintained its perfectly straight course, the case for active propulsion becomes very difficult to dismiss. The scientific community is waiting, carefully, quietly, with the kind of tension that builds when data keeps refusing to fit into the boxes we built for it. And there is one more detail that has not been discussed publicly yet. The object's trajectory does not just intersect the Milky Way's outer regions. When you trace it forward with enough precision, accounting for the galaxy's rotation and the Sun's orbit around the galactic center, the path comes closer than that, much closer. The Milky Way is enormous. It contains somewhere between 200 and 400 billion stars, depending on how you count them. It spans roughly 100,000 light-years from edge to edge. Our solar system sits about 26,000 light-years from the galactic center. In a quiet spiral arm called the Orion Spur, we orbit the center once every 230 million years, moving at about 220 kilometers per second. The object is moving at 400 kilometers per second. That is fast, but not extraordinary. Many stars in the galaxy's halo move faster. What makes the object's velocity significant is its direction. When researchers at the Harvard-Smithsonian Center for Astrophysics ran a detailed simulation of the object's trajectory, accounting for the Milky Way's gravitational field, the Sun's orbital motion, and the object's current velocity vector, they found something that triggered an immediate classified briefing to NASA leadership. The object's path, when traced forward over 3 million years, does not just pass through the Milky Way's outer halo. It passes within 2,000 light-years of the Sun's predicted position at the time of closest approach. 2,000 light-years is not close on a human scale. It is an incomprehensible distance, but on a galactic scale, it is extraordinarily precise. The Milky Way is 100,000 light-years across. The object's trajectory brings it within 2% of the galaxy's diameter of our solar system's future position. That is not a random intersection. That is a targeting precision that makes the coincidence explanation statistically uncomfortable. The research team ran the calculation multiple times, varying the assumptions about the object's velocity, the galaxy's rotation curve, and the uncertainties in both measurements. In every simulation, the closest approach distance remained between 1,500 and 3,000 light-years. The trajectory is robust. The intersection is real. The question is whether it means anything. Space is vast. Trajectories that look targeted from one perspective can be pure coincidence from another. The solar system is not stationary. In 3 million years, we will be in a completely different part of the galaxy than we are now. The object's trajectory was set long before our solar system even formed. The idea that it is aimed at us requires assuming that something launched it billions of years ago, with knowledge of where our solar system would be millions of years in the future. That requires precognition or an understanding of galactic dynamics so precise it borders on the supernatural. And yet the numbers are what they are. The trajectory intersects our path. The timing places the object in our neighborhood at a moment when we will be there, and the probability of that happening by chance, when you account for the size of the galaxy and the randomness of intergalactic trajectories is very small. One researcher, speaking on condition of anonymity, described it as unsettling but not impossible. That is about as close to alarm as scientists get in official settings. The classified briefing to NASA included recommendations. First, continue observations with all available assets. Second, begin preliminary modeling of potential close approach scenarios. Third, do not announce the trajectory intersection publicly until the data is confirmed beyond any reasonable doubt. That third recommendation was followed. The trajectory data has not been published. It exists in internal reports and restricted access databases. The teams working on it are under no formal gag order, but there is an unspoken agreement that releasing this information prematurely would cause exactly the kind of public reaction that makes continued scientific work difficult. The data will come out eventually. Science does not keep secrets well, and it should not, but for now, the intersection remains known only to a few dozen researchers and institutions funding the observations. The reason for the caution is simple. If the trajectory is confirmed, and if no natural explanation is found for how the object came to be on this path, the conversation shifts from "what is this?" to "what do we do about it?" 3 million years is a long time. It is longer than anatomically modern humans have existed. It is longer than most mammal species survive. But it is not infinite, and the object is not slowing down. We have encountered intergalactic objects before, twice. Both times the experience was humbling. The first was Oumuamua, detected in October 2017 by the Pan-STARRS telescope in Hawaii. It was the first confirmed object to pass through our solar system that originated from interstellar space. Not intergalactic interstellar. It came from another star system, entered our solar system at high speed, whipped around the sun, and shot back out into the void. Oumuamua was strange. Its shape was elongated, roughly 10 times longer than it was wide. It tumbled as it moved, reflecting light in a way that suggested a highly irregular surface, and it accelerated as it left the solar system. Slightly. The acceleration was tiny but measurable. Comets do this when they are heated by the sun and release gas which acts like a thruster, but Oumuamua showed no signs of outgassing. No tail, no cloud of gas or dust. Just a small, persistent acceleration with no obvious source. The scientific debate over Oumuamua lasted years. Some researchers argued it was a comet made of a material that outgassed in a way we did not recognize. Others suggested it was a fragment of a planet, broken apart by tidal forces near its home star and flung into space. A few, most notably Harvard astronomer Avi Loeb, suggested it might be artificial, a solar sail, a piece of alien technology. The idea was widely dismissed but never fully disproven. Follow-up observations were impossible. By the time astronomers realized how strange Oumuamua was, it had already left the inner solar system and was too faint to study in detail. It is gone now. Out of reach. The data we have is all we will ever have. The second object was 2I Borisov, detected in August 2019 by amateur astronomer Gennady Borisov. Unlike Oumuamua, Borisov behaved like a normal comet. It outgassed water vapor and carbon monoxide as it approached the sun. Its nucleus was a few hundred meters across, consistent with comets in our own solar system. Its trajectory was hyperbolic, confirming it came from interstellar space. But everything else about it was ordinary. Borisov was a relief. It showed that interstellar objects can be normal, natural, explicable. After the strangeness of Oumuamua, Borisov felt like a return to familiar ground. Both objects taught astronomers something important. Interstellar space is not empty. Objects cross the void between stars. Occasionally, they pass through our neighborhood. Most of them are probably ordinary comets, asteroids, fragments of planetary systems. We simply were not looking for them before. But some of them are not ordinary. Oumuamua proved that, and the object currently moving through intergalactic space, 300 million light-years away, is proving it again. The difference is scale. Oumuamua crossed through our solar system in a matter of months. We had weeks to study it before it disappeared. The object in intergalactic space is still 3 million years away from its closest approach. We have time. Time to study it. Time to understand it. Time to prepare, if preparation is necessary. That time is both a gift and a burden. The more we learn, the stranger the object becomes, and the questions it raises are not the kind that science is used to answering. Enrico Fermi asked his question in 1950 during a casual lunch conversation with colleagues at Los Alamos National Laboratory. The conversation had turned to UFOs and the possibility of extraterrestrial life. Fermi, one of the most brilliant physicists of his generation, posed a simple question that has haunted the scientific community ever since. Where is everybody? The logic is straightforward. The universe is roughly 13.8 billion years old. Our galaxy alone contains hundreds of billions of stars, many of them older than the Sun. If even a tiny fraction of those stars host planets capable of supporting life, and if even a tiny fraction of those planets develop intelligent life, and if even a tiny fraction of those civilizations reach the capability for interstellar travel, the galaxy should be full of evidence of their existence. We should see megastructures, Dyson spheres harvesting the energy of stars. We should detect radio signals, intentional or accidental, from civilizations broadcasting into space. We should find probes, self-replicating machines sent out to explore and report back. Given the age of the galaxy and the speed at which even slow interstellar probes could spread, every star system should have been visited by now. And yet we see nothing. The sky is silent. No signals, no structures, no visitors. The Fermi paradox is not a paradox in the formal logical sense. It is a question wrapped in uncomfortable silence. Dozens of explanations have been proposed. The Great Filter suggests that some catastrophic barrier prevents most civilizations from reaching interstellar capability. Maybe it is nuclear war. Maybe it is climate collapse. Maybe it is something we have not encountered yet. The zoo hypothesis suggests that advanced civilizations know about us but are deliberately avoiding contact, observing us from a distance. The dark forest theory, popularized by science fiction but taken seriously by some researchers, suggests that the galaxy is full of civilizations, but they all remain silent because revealing your location is dangerous. None of these explanations are satisfying. All of them are speculative. And the silence continues. The object moving through intergalactic space does not answer the Fermi paradox, but it reframes it in a way that is deeply uncomfortable. If the object is natural, it is an extraordinary coincidence that we are detecting it now, moving on a trajectory that will bring it into our galaxy at a time when we have just developed the technology to see it. The universe is 13.8 billion years old. Human civilization has existed for a blink of that time. The odds that this object happens to be passing by now, close enough and visible enough for us to detect, are vanishingly small. If the object is artificial, the Fermi paradox shifts. We are no longer asking why we see no evidence of extraterrestrial civilizations. We are asking why this evidence is moving through empty space 300 million light-years from the nearest galaxy, broadcasting a signal at the hydrogen line frequency on a trajectory that intersects our path. Both possibilities are difficult to accept. One requires believing in an extraordinary coincidence. The other requires believing we are not alone and that something out there launched an object millions of years ago that is now approaching us. Science does not deal in belief. It deals in evidence. The evidence is incomplete. The object exists. It is moving. It is emitting signals. The reason for all of that remains unknown. And the next round of observations may finally provide the answer, or it may provide more questions. That is how science works. You point your instruments at the unknown. You gather data and you follow where it leads, even when it leads somewhere you were not expecting. The object is still out there, still moving, still broadcasting. And in 3 months we will know more. There is a frequency that every radio astronomer knows by heart, 1420.4058 MHz. It is the frequency at which neutral hydrogen emits radio waves. The hydrogen line, it is the most common spectral line in the universe because hydrogen is the most common element in the universe. When a hydrogen atom's electron flips from one spin state to another, it releases a tiny amount of energy in the form of a radio wave photon at precisely this frequency. The process is quantum mechanical, probabilistic, and incredibly rare for any individual atom. But when you have vast clouds of hydrogen gas containing trillions upon trillions of atoms, a collective emission is strong enough to detect from across the universe. Radio astronomers use the hydrogen line to map the distribution of gas in and between galaxies. It is a tool for tracing structure, measuring velocity, and understanding the large-scale architecture of the cosmos. It is also the frequency that SETI researchers monitor most carefully. In 1959, physicists Giuseppe Cocconi and Philip Morrison published a paper in the journal Nature titled Searching for Interstellar Communications. In it, they argued that any civilization attempting to communicate across interstellar distances would likely broadcast at the hydrogen line frequency, not because hydrogen is special in any way other than its abundance, but because any scientifically literate civilization would recognize it as a universal constant, a natural marker in the electromagnetic spectrum that says, this is not random noise, this is deliberate. The logic is simple. If you want to send a signal that will be noticed, you broadcast at a frequency that anyone listening would already be monitoring. The hydrogen line is that frequency. It is the cosmic calling card. The object moving through intergalactic space is broadcasting at 1420.4 MHz, not approximately, precisely, to within the measurement accuracy of the radio telescopes observing it. That could be a coincidence. The object could be emitting hydrogen gas, and that gas could be fluorescing naturally at the hydrogen line frequency. Gas clouds throughout the universe do this all the time. It is entirely normal. But the emission is not coming from a diffuse cloud. It is coming from a point source, a compact object, and the modulation, that 4.3-hour periodic variation in intensity, is not something natural hydrogen clouds produce. The signal has been analyzed for patterns, the kind of patterns that would indicate embedded information. Pulses within the modulation, variations in frequency or phase, anything that might carry a message. So far, nothing has been found. The signal is periodic, stable, and clean. It rises and falls smoothly over 4.3 hours, then repeats, over and over. That simplicity is either evidence of a natural origin or evidence of a signal designed to be noticed but not decoded. A beacon, not a message. SETI has protocols for this. When a candidate signal is detected, it is subjected to a series of tests. First, confirm that it is not terrestrial interference. Satellites, radar, cell towers, and terrestrial radio sources produce signals that can mimic astronomical sources if you are not careful. This signal is confirmed as astronomical. It does not match any known terrestrial source, and its position in the sky is fixed relative to the distant stars, not moving with Earth's rotation. Second, confirm that it is not a known natural source. Pulsars, quasars, magnetars, and other astrophysical objects emit radio signals. This signal does not match the profile of any known natural source. Third, look for modulation or information content. This is where the analysis is ongoing. The 4.3-hour periodicity is clear. Whether there is additional structure beneath that periodicity is still being determined. Fourth, attempt to localize the source as precisely as possible and gather multi-wavelength data. Webb has provided optical and infrared data. Radio telescopes have provided precise positional information. The source is real, localized, and multi-wavelength. It passes all the tests so far. The final step is replication. Other observatories must confirm the signal independently. That has happened. The VLA, the Australian SKA Pathfinder, and the Meerkat Array in South Africa have all detected the signal. It is real. What SETI has not done is announce this as a confirmed extraterrestrial signal, because it is not. Not yet. The probability that it is natural, while decreasing with each new observation, is still higher than the probability that it is artificial. Science requires extraordinary evidence for extraordinary claims. The evidence is building. It is not yet extraordinary, but the frequency is 1420.4 MHz, the hydrogen line, the universal channel. If something wanted to be noticed, this is where it would broadcast, and it is broadcasting, continuously. For millions of years, 3 million years is incomprehensible to human minds. Our species, Homo sapiens, has existed in an atomically modern form for roughly 300,000 years. Recorded human history stretches back only about 5,000 years, the longest lived human civilizations. Egypt, Mesopotamia. China lasted a few thousand years before transforming into something unrecognizable to their founders. 3 million years ago, our ancestors were Australopithecus, upright walkers, tool users, not yet human. The gap between them and us is enormous. Language, art, science, cities, spaceflight, all of it happened in the blink of time between then and now. 3 million years in the future is equally unimaginable. If humanity survives, we will be something else entirely. The species that exists then will look back at us the way we look at Australopithecus. If we do not survive, something else will fill the niche. Evolution does not stop. The object has been traveling for at least 100 million years, possibly much longer. It left its origin point when dinosaurs walked the Earth. It crossed the void while continents split apart and oceans formed. It kept moving while mammals evolved, while ice ages came and went, while our ancestors climbed down from trees and learned to walk upright. If it is artificial, it was built by a civilization that no longer exists in any form we would recognize. If it is still operational, it has outlived its creators by an unimaginable span of time. That longevity is the single most striking feature of the object. Not its size, not its trajectory, its endurance. Human spacecraft are fragile. Voyager 1, the most distant human-made object, was launched in 1977. It is now over 15 billion miles from Earth in interstellar space, still transmitting data. Its plutonium power source will run out around 2025. After that, it will go silent. It will continue coasting through space indefinitely, but it will be dead. A relic. In a few tens of thousands of years, it will pass near another star. By then, it will be frozen, radiation-scarred and inert. The object in intergalactic space has been traveling for millions of years and is still active, still emitting signals, still, possibly, maintaining its trajectory, whatever it is made of, however it is powered. It was built to last in a way that no human technology has ever approached. That durability suggests purpose. Natural objects do not need to last, they simply exist until they do not. Artificial objects built for a purpose are designed to endure long enough to fulfill that purpose. The object has endured for 100 million years. What purpose requires that kind of timescale? One possibility, it is a probe, an exploration mission sent out by a civilization that understood it would take millions of years to reach its destination. The civilization that launched it is gone. The probe continues. Patient, autonomous, crossing the void because that is what it was built to do. Another possibility, it is a message in a bottle, not designed to reach a specific destination, but to travel until it is found, a monument to a dead civilization. Proof that they existed. Sent out into the universe because that was the only way to ensure something of them would survive. A third possibility. It is a seed, carrying information, technology, or even biological material, designed to reach another star system and begin, again, a backup, insurance against extinction. All of these are speculation. But they are not wild speculation. They are the kind of thing a sufficiently advanced civilization might do if it understood the timescales involved in crossing intergalactic space and had the technology to attempt it. We are attempting it. Voyager is humanity's version of the same idea. A message in a bottle, sent out in the hope that someday, millions of years from now, something will find it and know we were here. The difference is that Voyager is silent now, or will be soon. The object in intergalactic space is still broadcasting, and that raises the most uncomfortable question of all. If it has been traveling for 100 million years, why is it still powered? Every spacecraft humans have ever built faces the same fundamental constraint: power. You can carry batteries, but they run out. You can carry solar panels, but they only work near a star. You can carry a nuclear reactor, but even plutonium decays and eventually produces too little heat to generate electricity. Voyager's plutonium-238 power source has a half-life of 87.7 years. After that time, half of the plutonium has decayed into uranium-234, and the heat output has dropped by half. After 200 years, the heat output is negligible. Voyager will be powerless long before it reaches another star. The object has been traveling for at least 100 million years. If it is still powered, it is using something far more durable than any power source we know how to build. There are theoretical possibilities. Certain isotopes with extremely long half-lives could provide power for millions of years. Thorium-232 has a half-life of 14 billion years. Uranium-238 has a half-life of 4.5 billion years. An object with a core made of these isotopes, surrounded by thermoelectric converters to turn heat into electricity, could theoretically remain powered for geological timescales, but the energy output would be extraordinarily low. Radioactive decay produces heat slowly. Over millions of years, even a large mass of uranium would produce only a trickle of power, enough to keep a small transmitter running, enough to maintain minimal systems, not much more. The object's radio emission is faint but continuous. The power required to produce it is on the order of a few watts, a light bulb's worth. That is well within what long-lived radioactive isotopes could provide, but the hydrogen emission is harder to explain. If the object is actively venting hydrogen gas, that gas has to come from somewhere. Either it is carrying a reservoir of hydrogen that has somehow remained stable for 100 million years, which is difficult to reconcile with physics, or it is producing hydrogen. Producing hydrogen requires energy. If the hydrogen is being generated by some chemical or nuclear process inside the object, that process needs fuel. Fuel that has lasted 100 million years. The only known processes that can sustain energy production on that time scale are nuclear, fission, fusion, or radioactive decay. Fission and fusion were radioactive decay. Fission and fusion require fuel that must be consumed. Radioactive decay is passive but produces only heat, not hydrogen. There is another possibility, one that researchers are reluctant to discuss publicly because it sounds too much like science fiction, but it is theoretically possible and it fits the data. The object could be harvesting energy from the cosmic microwave background. The cosmic microwave background is the faint radiation left over from the Big Bang. It fills all of space uniformly, with a temperature of roughly 2.7 Kelvin. That is cold, close to absolute zero, but it is not zero. And in thermodynamics, any temperature difference can, in principle, be used to extract energy. A sufficiently advanced heat engine to use the temperature difference between the object's interior and the surrounding cosmic microwave background to generate power. The efficiency would be extraordinarily low. The amount of power generated would be tiny, but over millions of years, a tiny trickle of power is enough. This is not technology humans possess. It is not even technology we know how to build in theory. But the laws of thermodynamics do not forbid it, and if the object has been traveling for 100 million years, it is not unreasonable to assume that whoever built it, if anyone did had access to technology, we do not yet understand. The alternative is that the object is not powered at all, that the radio emission and the hydrogen cloud are purely natural phenomena that we are misinterpreting as artificial. That is still the most probable explanation, the null hypothesis, the default assumption until evidence proves otherwise. But the evidence keeps accumulating, and it keeps pointing the other way. The next observation window opens in 47 days. Webb will observe the object for a continuous 72-hour period, the longest single observation ever allocated to a target outside our own galaxy. The goal is simple: gather enough data to resolve the remaining uncertainties. Webb will measure the hydrogen emission in unprecedented detail. The spectrograph will analyze the gas's temperature, velocity, and chemical composition. If there are trace elements mixed with the hydrogen, carbon, nitrogen, oxygen, Webb will detect them. If the gas is being heated by an internal source, the temperature will reveal that. If it is simply venting cold from the object's interior, that will be clear too. Webb will also measure the object's rotation with far greater precision than before. If the 4.3-hour period is slowing down, even by milliseconds per year, Webb will see it. If it is perfectly stable, that too will be definitive, and Webb will search for additional signals. Infrared emission beyond what has already been detected, variations in brightness that might indicate surface features rotating in and out of view. Any asymmetry in the object's light that could tell us about its shape or structure. The data will arrive in early 2025. It will be processed immediately. and the results will be published, regardless of what they show. If the object is natural, the paper will explain how. It will propose a mechanism outgassing driven by internal radioactive heat, or a fragment of a destroyed planet, or something else entirely. It will close the book on this mystery and file it away as an extraordinary but explicable phenomenon. If the object is not natural, the paper will not say that directly. Science does not work that way. It will say the object's properties are inconsistent with known natural mechanisms. It will say further investigation is required. It will recommend follow-up observations and theoretical work. And behind the scenes, quietly, the conversation will shift. Not publicly, not yet, but within the community. The possibility that we are observing something artificial will move from fringe speculation to serious hypothesis. That shift has already begun. Conversations that would have been unthinkable 5 years ago are happening now in private emails, restricted meetings, and classified briefings. Researchers are asking questions they were trained never to ask. What if it is artificial? What if it was sent here deliberately? What if we are being contacted and we just did not recognize it until now? These are not the questions science is designed to answer. Science answers questions about how the universe works. It does not answer questions about intention, purpose, or meaning. Those are philosophical questions, human questions. But when the data keeps pointing towards something that looks intentional, philosophy and science collide. And that collision is happening now. If the object is artificial, the silence around it is deafening. There is no accompanying signal explaining what it is. No message encoded in the radio emission. No response when we pointed our most powerful transmitters at it and sent signals in return. Just a steady 4.3-hour modulation, rising and falling, repeating. That silence is consistent with a probe or a beacon, something designed to be noticed, not to communicate. A marker, a signpost. We were here, we did this. This is proof, but it is also consistent with something far stranger. A transmission not meant for us. A signal being broadcast to something else, and we are simply overhearing it. If the object is a probe sent by a civilization millions of years ago, it was not sent for our benefit. We did not exist when it was launched. Our sun was already burning, but the Earth was a barren rock. No life, no oceans, nothing to contact. If it is approaching us now, the timing is coincidence. It was aimed at this region of space long before we were here. And if it is transmitting because that is what it was programmed to do. Not because it knows we are listening. That possibility is somehow more unsettling than deliberate contact. It suggests a universe where we are not significant, where vast engineering projects cross the void and we are simply in the way, witnesses to something not meant for us. There is also the possibility that the object is not alone, that it is one of many, a network, probes scattered across intergalactic space, broadcasting to each other, relaying information across distances too vast for any single signal to cross. If that is true, we are detecting the edge of something enormous, an infrastructure built on timescales and distance scales that dwarf anything in human experience. The 3 candidate detections mentioned earlier, the faint signals flagged in archival data, are being followed up now. If they are confirmed as similar objects, the network hypothesis becomes considerably more plausible. And if there is a network, it raises the question, what is it for? What purpose requires spreading objects across intergalactic space, broadcasting continuously for millions of years? One possibility, navigation. The objects are beacons marking routes to the universe, guiding something. Another, communication. The objects are relay stations passing messages across distances no single transmission could cross. A third, monitoring. The objects are sensors, gathering data about the universe and transmitting it somewhere. All of these require a civilization with capabilities so far beyond ours that comparison is meaningless. A civilization that thinks in time scales of millions of years, that builds for durability we cannot imagine, that operates on scales we are only now beginning to detect. If such a civilization exists or existed, we are not their equals. We are barely their contemporaries. We are children, stumbling onto artifacts left behind by adults, and the object is still moving toward us, 3 million years. That is the time remaining until closest approach. It sounds safe, distant, abstract, but astronomical timescales are not human timescales. 3 million years is soon. In cosmic terms, it is imminent. And we do not know what happens when the object reaches the Milky Way. We do not know if it will pass through harmlessly, a traveler moving on to the next destination. We do not know if it will slow down. We do not know if it will interact with anything. The models predict a closest approach of 2,000 light-years from the Sun's future position. That is far enough that no direct interaction is likely. Space is vast. Even passing through the galaxy's outer halo, the object will not encounter anything. Stars are separated by light-years. The chance of a collision is effectively zero, but that assumes the object is inert, a piece of rock and metal coasting on momentum. If the object is active, the calculation changes. If it can alter its trajectory, even slightly, it can choose where it goes, and if it is transmitting, if it is aware, if it is searching, then its path is not fixed. It is a decision. We have no evidence that the object is capable of changing course. Its trajectory has been perfectly straight for as long as we have observed it. But we have only been observing it for 3 years. That is nothing. A snapshot. We do not know what it has done in the past, and we do not know what it will do in the future. The classified briefing to NASA included worst-case scenarios, not because anyone believes they are likely, but because planning for low-probability, high-impact events is what institutions do. Scenario 1. The object enters the Milky Way and remains on its current trajectory. Closest approach to the Sun is 2,000 light-years. No interaction, no threat. It passes through, exits the galaxy, and continues into the void beyond. We observe it for as long as we can, then lose track of it as it fades into the distance. The mystery remains unsolved, but we survive. Scenario 2. The object alters course. It changes trajectory to pass closer to regions of higher stellar density. Perhaps it is searching for something. Perhaps it is mapping the galaxy. Perhaps it is doing something we cannot predict. It does not threaten Earth directly, but its presence raises questions we are not prepared to answer. Scenario 3. The object approaches a star system and interacts with it. Not our Sun, some other system. We observe from a distance. We see what it does. We learn something about its purpose, and we prepare for the possibility that it might do the same to us someday. Scenario 4 is not discussed in official documents. It is discussed quietly, in private conversations. The object approaches our solar system, not in 3 million years, sooner. It changes course. It accelerates. It arrives in our lifetime, or our children's lifetime, or within the span of recorded human history. That scenario requires capabilities we have no evidence the object possesses. Active propulsion far beyond the tiny hydrogen venting we have detected. Power sources orders of magnitude beyond radioactive decay. Awareness of our presence. But if the object is artificial, and if it has endured for 100 million years, it is not unreasonable to assume it can do things we do not expect. And if it can, the question becomes, what does it want? Science is built on questions that can be tested, hypotheses that can be confirmed or falsified through observation and experiment. What is the object made of? Is a scientific question. We can measure its spectrum and determine its composition. How fast is it moving is a scientific question. We can measure its position over time and calculate its velocity. What does it want is not a scientific question. It assumes intention, purpose, consciousness. Those are not things science can measure. And yet, if the object is artificial, the question is unavoidable. Something built it. Someone launched it. And they did so for a reason. We may never know that reason. The civilization that launched it is almost certainly gone. Even if they survived, they are 300 million light-years away, separated from us by a gulf of space so vast that communication is impossible. A signal sent today would take 300 million years to reach them. Their reply would take another 300 million years to return. By the time we received it, humanity would be gone. The Sun would be gone. The Earth would be a cold, dead rock orbiting a white dwarf star. The object itself may carry the answer. If it is a probe, it may have recordings, data, instructions, a message explaining what it is and why it was sent. But extracting that information requires intercepting the object, and the object is 300 million light-years away, moving at 400 kilometers per second. We cannot reach it, not with any technology we possess or will possess in the foreseeable future. Even if we could, we do not know how to communicate with it. We do not know its protocols. We do not know its language. We do not even know if language is a concept it would understand. The object has been broadcasting for millions of years. We have been listening for 3. In that time, we have detected a periodic signal at the hydrogen line frequency. Nothing more. No variation that suggests response. No change that indicates awareness of our observations. Either it does not know we are here, or it does not care. Both possibilities are humbling. We like to imagine that contact with extraterrestrial intelligence would be a momentous event, a conversation, an exchange of ideas, first contact. But the object is not here for us. It was launched before we existed. It will pass through our galaxy and continue on, indifferent to whether we noticed it. We are not participants in whatever purpose it serves. We are witnesses, and even that may be generous. The universe does not care about us. That is a fact that astronomy teaches more clearly than any other science. We are not at the center. We are not special. We are one planet among billions, orbiting one star among hundreds of billions, in one galaxy among trillions. The odds that any particular cosmic event is about us are vanishingly small, and yet we cannot help but ask, why is it coming here? Why now? Why this trajectory of all the infinite possible trajectories across intergalactic space? The answer may be nothing more than mathematics, gravity, momentum, random chance over incomprehensible spans of time. Or it may be something else. We do not know, and the not knowing is where we are forced to sit. If the object is artificial, it changes everything we thought we knew about the prevalence of intelligent life in the universe. The Fermi paradox rests on a simple observation. The universe is old and vast, and we see no evidence of other civilizations. That silence suggests either that intelligence is extraordinarily rare, or that civilizations do not last long enough to spread across the stars, or that they exist but remain hidden for reasons we do not understand. The object, if artificial, is evidence, not of a living civilization, but of one that existed, one that built something designed to outlast its creators by millions of years, one that had the capability to launch objects across intergalactic space. That capability is staggering. The energy required to accelerate even a small object to intergalactic escape velocity is enormous. The precision required to aim it at a target 300 million light-years away is beyond anything humans can currently achieve. The engineering required to build something that functions for 100 million years is so far beyond our capabilities that we do not even have a theoretical framework for attempting it. If one civilization achieved this, others likely did as well. If intergalactic probes exist, they may not be rare. They may be common. We may simply be detecting one of many because we are finally looking in the right way with the right instruments. The square kilometer array, when it reaches full operational capacity, will be sensitive enough to detect signals far fainter than anything we can see now. If there are other objects like this one scattered through intergalactic space, SETI will find them, and if it does, the picture changes entirely. We are not alone. We were never alone. The universe has been full of intelligence, building, launching, transmitting across timescales that make human history look like a blink. The fact that we see no living civilizations becomes less mysterious. Civilizations rise and fall. Stars burn out. Galaxies collide. Over hundreds of millions of years, nothing biological survives unchanged. But the things they build can. The object may be one of countless monuments, tombstones, proof that someone was here, even if they are here no longer. That should be terrifying. It suggests that intelligence, no matter how advanced, does not survive, that the universe is a graveyard of dead civilizations, and we are simply the latest to arrive. But it is also hopeful, because they tried. They built something that would outlast them. They sent it out into the void, knowing they would never see it arrive. They did it anyway, and we found it. That means we are capable of the same. If humanity does not survive, if we destroy ourselves or are destroyed by something beyond our control, we can still leave something behind. A signal, a probe, a message. Voyager is already doing that. It carries the golden record, a collection of sounds and images from Earth. Encoded on a gold-plated disc, the record includes greetings in 55 languages, music from different cultures, and 116 images showing life on Earth. It was designed to be found by an alien intelligence millions of years from now, long after we're gone. The object in intergalactic space may be someone else's golden record, a message in a bottle, cast into the cosmic ocean, carrying the memory of a world that no longer exists. If that is what it is, we owe it to its creators to listen. There is a question that has not been asked publicly yet, but is being debated behind closed doors. If the object enters the Milky Way in 3 million years, and if we are still here, what do we do? 3 million years is long enough that the question seems abstract. Humanity will be unrecognizable by then, if it exists at all. But the question is not really about 3 million years from now, it is about now. About what we choose to do with the knowledge we have. Do we attempt contact? The object is 300 million light years away. Any signal we send will take 300 million years to reach it. There is no possibility of a conversation. But we could send a message anyway. We are here. We see you. We acknowledge you. Some researchers argue we should, that if the object is artificial, its creators deserve to know their work was seen, that even if the message arrives long after both civilizations are gone, it is the right thing to do. Others argue against it, that broadcasting our presence to an unknown object whose purpose we do not understand is reckless, that we should observe, learn, and say nothing until we know more. The debate mirrors the larger SETI debate about active messaging. Should we transmit signals into space, announcing our presence to anyone listening? Or should we remain silent, listening but not speaking, until we understand the risks? There is no consensus. And there will not be. The decision, if it is made at all, will be made by institutions, governments, and individuals with their own agendas. Science can inform the decision. It cannot make it. What is clear is that the object has already changed us. The simple fact of its existence, the questions it raises, the possibilities it represents, all of that has shifted how we think about our place in the universe. We are not the first. That is the inescapable conclusion. Whether the object is natural or artificial, whether it is ancient or recent, whether it is directed at us or indifferent to us, it proves that extraordinary things cross the void, that the universe is richer and stranger than we imagined. And if the object is artificial, it proves something even more profound, that intelligence can endure, that the work of minds can outlast the bodies that created them, that the universe remembers. That is not a scientific statement. It is a human one, but it is the statement the object demands we confront. The next 2 years will be critical. Webb's observations in early 2025 will provide the most detailed data we have ever had on the object. If there are answers to be found in the light it emits, Webb will find them. The follow-up observations of the 3 candidate objects will also be completed by late 2025. If those objects are confirmed as similar to the first, the conversation shifts immediately. 1 anomalous object is a mystery. 4 is a pattern. Patterns demand explanations. The Square Kilometre Array will begin early science operations in 2027. When it does, it will survey vast regions of intergalactic space with sensitivity far beyond anything currently available. If there are more objects like this one, SKA will detect them, and the catalogue will grow. Each new detection will add constraints, trajectories, velocities, signal characteristics. The more objects we find, the clearer the picture becomes. Are they moving randomly, or do their paths show structure? Are they broadcasting the same signal, or different ones? Are they all the same age, or do they span a range of launch dates? These questions have answers. The answers are already written into the light traveling toward us. We simply have to wait for it to arrive. Within 5 years, we will know whether the object is alone or part of a population. We will know whether its trajectory is unique or part of a pattern. We will know whether the hydrogen emission is natural or artificial. We will know whether the 4.3-hour period is stable or decaying. We will not know everything. Science never does, but we will know enough to move the conversation forward, to refine the questions, to narrow the possibilities, and if the evidence keeps pointing in the same direction, the scientific community will be forced to confront a conclusion it has been avoiding. We are not alone. We have never been alone. The universe is full of the remnants of intelligence, and one of those remnants is moving toward us. There is a question beneath all the others, a question that science cannot answer, but that every human being asks when they look up at the night sky. Are we significant? The object, whatever it is, does not care about that question. It was not built to answer it. It exists, it moves, it transmits, that is all. But we care. We cannot help but care. Because the question of our significance is the question of our meaning. It is the question that drives art, religion, philosophy, and science. It is the question that every civilization, everywhere, must eventually ask. If the universe is empty, if we are alone, we are significant by default. We are the only thing that matters because we are the only thing that thinks. If the universe is full, if intelligence is common, we are not significant. We are one voice among billions. One experiment among countless others. Replaceable, forgettable. The object suggests the second possibility, that we are not unique, that intelligence arises, builds, transmits, and fades, over and over, across the universe, across time. We are not the first, and we will not be the last. That should make us feel small, insignificant, lost in the vastness. But there is another way to see it. If intelligence is common, if the universe is full of minds that think and build and wonder, then we are not alone. We are part of something larger, a community, separated by space and time, but connected by the simple fact of existence. The object, if it is artificial, was built by someone who looked up at their sky and asked the same questions we ask, who wondered if anyone else was out there, who decided to send something into the void, hoping it would be found. We found it, and in finding it, we answered their question. Yes, someone else is here. We are here. We see what you made. We acknowledge it. We remember. That is what the object gives us if we choose to accept it. Not proof of contact, not communication, not answers, connection. Across 300 million light years, across 100 million years of travel, across the death of stars and the birth of worlds, someone was here. They reached out, and we reached back. That is the story the object tells, not in radio signals or hydrogen clouds or trajectories, but in the simple fact of its existence. The universe is not empty. It has never been empty. And we are part of it. Science will continue. Observations will accumulate. Papers will be published. The object will be studied until we understand it as well as we can, given the distance and the limitations of our instruments. And then the object will move on. It will continue its journey indifferent to our attention. In 3 million years, it will pass through the Milky Way. We will not be here to see it, not as we are now. But perhaps something of us will remain. Perhaps our descendants, biological or otherwise, will point their instruments at it and remember that their ancestors once wondered what it was. Perhaps they will know the answer. Perhaps they will build their own objects and send them into the void, continuing the cycle, reaching out, hoping to be found. Or perhaps they will be gone and the object will pass through an empty galaxy, transmitting to no one. Both possibilities are real. Both are within the range of outcomes that the universe allows. What we do between now and then matters, not to the object, not to the universe, but to us. Because the object is not just a mystery to be solved, it is a mirror. It shows us what we could become, what we could build, what we could leave behind. We are young, we are fragile, we have existed for a blink of cosmic time, and we may not exist for much longer. But while we are here, we can choose to reach out, to build, to transmit, to say, we were here, We thought, we wondered, we tried. That is what the object is saying. Across 300 million light years, across 100 million years of silence, and if we listen carefully enough, we can hear it. The universe is older than we thought, richer than we imagined, full of things we are only beginning to see. 3 years ago, astronomers pointed their instruments at a faint radio signal in intergalactic space. What they found was a small object moving through the void, broadcasting at the hydrogen line frequency on a trajectory that will bring it into our galaxy in 3 million years. We do not know what it is, not yet, but we are learning. Every observation brings us closer. Every data point narrows the possibilities, natural or artificial, ancient or recent, directed or random. The answer is coming. It is written in light that left the object millions of years ago, traveling toward us at the speed of the universe allows. When that light arrives, when we decode it fully, we will know, and whatever the answer is, it will change us. Because the question itself has already changed us. It has forced us to confront the possibility that we are not alone, that we have never been alone, that the universe is full of minds that think and build and wonder. The object is still out there, still moving, still broadcasting, and we are still listening. If you want to go deeper into what happens when the data finally arrives, when the picture becomes clear, when we are forced to confront the answer we have been avoiding, we keep going in the next one. But for now, sit with this. Something is moving through deep space. It is getting closer. And in the silence between stars across distances that dwarf comprehension, it is saying something. We just have to decide whether we are ready to hear it.